Well, we're going to shift gears a little bit here now. We're going from implementation and testing of an AM HD radio signal. Now we're going to talk about research and development for the FM HD radio signal. So I'm going to review the results of our research that we've been performing over, say, the last 3 or 4 years to improve the performance of the FM HD radio signal. So, in recent years, the HD radio stakeholders have expressed a desire for us to increase both the capacity and the robustness of the HD radio signal. Now, these are two competing objectives. So, what we've done is we've developed a set of new service modes that are very flexible and will allow the broadcaster to trade these two parameters. Now, we spent, as I said, a long time doing extensive research. We've fully analyzed, designed, modeled, simulated, and even prototyped these service modes. And we've done it because we want to make sure that we enhance the viability of the HD radio signal going into the future. We want to make sure that we maintain the relevance of radio in the connected car. But as we do this, it's very important that we have a smooth transition. There's more than 50 million HD radio receivers on the road right now. And we have to make sure we maintain backward compatibility, especially in North America. However, if we weren't constrained by backward compatibility, we could develop even stronger service modes. And that's actually what we did. We developed some non-backward compatible service modes as well. And those service modes could be used, for instance, for new data applications, such as autonomous vehicles. We could also use them for international applications. And finally, once the service modes have been in the field long enough, even in North America, broadcasters could decide to turn those service modes on. Now, I have to make the statement that this is all currently just in the research and development phase. We do not have a formal commercialization effort yet. And any modifications that we made to the HD radio standard would have to be reviewed by the NRSC. Before I talk actually about what the waveforms look like, let's discuss some of the key design characteristics that are common to all these new waveforms. And some of these characteristics are actually a part of the existing HD radio waveforms, such as orthogonal frequency division multiplexing, or OFDM. It's just a digital modulation and multiplexing scheme. It's very popular in digital communication systems, especially mobile systems, and not only HD radio, but systems like Wi-Fi use it. And as you can see here in the stylized spectrum here, we have an analog host that's flanked on either side by digital sidebands. And a standard digital signal uses a single wide bandwidth carrier to transmit the digital. With OFDM, it uses multiple narrow band subcarriers to do that. And you can see that in the picture here. One thing we have to make sure of is that we fall within the existing FCC spectral mask with our sidebands, and we maintain all the existing protection ratios. We chose OFDM because of its strong resistance to multipath fading. But we also like it because of its inherent flexibility. We can turn on and off subcarriers, and we can assign code bits to the subcarriers very easily. So frequency diversity is another technique that we've used with the existing service modes, and we use it now with our new service modes. The FM broadcast channel, as many of you probably know, is characterized by frequency selective multipath and non-uniform interference. And you can see that, oops, wrong button. You can see that here. We have here's an FM hybrid signal, and you can see the lower sideband has a big notch in it, and the upper sideband appears relatively unaffected. And over time, in a moving vehicle, you can see what this looks like. it's kind of a mess. The sidebands are sometimes they're the same, sometimes they're different. So what we do is we simulcast the same digital content. The information goes on the upper sideband and the lower sideband to combat this. And we can use special forward error correction coding techniques then to get that information back off of one sideband, even when the other sideband is completely corrupted. So just as we use the upper and lower sidebands for frequency diversity, we also use time-diverse main and backup components of the digital signal to provide time diversity. And this time diversity is important for combating the effects of signal outages that are caused by things like terrain or buildings or overpasses and bridges. So we already do something like this in the hybrid system. Our backup signal is actually just the delayed analog signal, and the main signal is the MPS digital signal. And we blend back and forth between the analog and digital signal depending on the quality of the digital. So now with our new service modes, those main and backup channels are fully digital. And the backup channel is actually lightly interleaved. And that's so that we can use it for fast tuning. And that's important when you don't have an analog backup, say with an all digital signal or with a multicast channel. As you may know, tuning to multicast channels takes time for the channel to be decoded. So this would take care of that. You can look at this diagram here just to show how time diversity works. It's just a sequence of audio and data packets that are shifted in time. And since over the air, the impairment is going to affect the main and backup channel in different places in their audio, so that when we align them at the receiver, they basically act as gap fillers. One fills in for the other, and it's a very effective technique. Okay, so we have lower and upper sidebands providing frequency diversity, main and backup components providing time diversity. This is actually very important. It's a two-dimensional diversity scheme that we've found over the years is extremely important for the robustness of an HD radio signal. So that lower upper main backup, or LUMB diversity, is what we use. So what we had to do, though, is develop a forward error correction code that can take advantage of this two-dimensional diversity. And we did that using something called complementary punctured pair convolutional coding. And I'm getting way ahead of myself here. Okay, there we go. So forward error correction coding is just you're adding redundancy to the digital signal so that you can detect and correct bit errors that are engendered by the channel. So this forward error correction code that we use, CPPC, is a single composite code that protects all four of these diversity components, the L, the U, the M, and the B. So what's good about this code is that each of the components, each of those four components, is also protected by a standalone subset of that composite code, such that if those components are independently decodable. And why is that important? Well, if you happen to lose a sideband due to selective fading, for instance, you can still receive the other sideband. You can still get the information content from the other sideband. Or if you go through an outage, say you lose your main component, you can still receive the signal on the backup component. So basically, we've designed a diversity scheme and our forward error correction coding to combat the effects of the channel that we know are cause the most degradation to the FM signal. In addition, we use a Reed-Solomon concatenated code to further improve the robustness. We have to add parity bytes for this, so it reduces our information throughput by about 6%. However, it also reduces the required signal power by 30%. So we think this is a pretty good bargain. Now, everything I've talked about up till now has been techniques we use to improve the robustness of the HD radio signal. But how do we actually improve the capacity? And we do that using a higher order modulation scheme known as QAM, or quadrature amplitude modulation. Uh-oh. Okay, so with our existing system, we modulate each OFDM subcarrier with 2 bits. And that ends up creating 4 constellation points. And that's why we call it a 4-QAM signal, or QPSK. Now, we could double the throughput and get 16 constellation points. That's called 16-QAM, or we could even triple it and get 64 constellation points, what we call 64-QAM. Well, when you do this, what you notice here is we're jamming more and more information into the same signal space. And that causes these constellation points to jam closer together, and it makes it harder and harder for receivers to distinguish one from the other, especially in noise. So in general, when you move to higher order modulations, you're going to lose a fair amount of robustness. But what we've done here is we've developed special trellis-coded modulation techniques along with channel state estimation techniques that actually make this higher order modulation feasible for HD radio. So in summary, we use QAM, higher order QAM, to increase the capacity. We use two-dimensional diversity with special coding techniques in Reed-Solomon to improve the robustness. We have fast tuning now on our backup channel, so that helps with multicast tuning time. And we're very confident that all this is going to work because service modes MP5 and MP6, those are existing service modes for all digital. Those service modes have used similar techniques that I've been talking about, and they were shown in field tests in Korea in 2012 to significantly outperform all of our other existing modes and many of the other systems, digital radio systems that we tested against. So now that I've described how we build these service modes, let's talk about what they actually are, what the structure of them is. And we'll start with our backward compatible service modes. And the first one is service mode MP3X, which is not surprisingly backward compatible with service mode MP3. And here's a spectrum. I did it again. Here. There we go. Here's a spectrum of hybrid signal. You can see the analog host in the center and the 2 digital sidebands on either side. All hybrid signals in their primary main spectrum. There's 10 partitions where they broadcast the P1 logical channel, and that channel generally has the main program service digital. Now, in service mode MP3, they add an additional 2 partitions in the extended region on each side to get an extra 25 kilobits per second of throughput. And all we did with service mode MP3X is add 2 more of those extended partitions, and we use instead the more robust P4 logical channel. And so that new logical channel provides an additional 17 kilobits per second, 34 or 46, depending on which order of the modulation we use. So we have another backward compatibility mode, which is we call MP1X, and surprise, it's backward compatible with MP1. And we like this mode the best because we can now use all 4 of our extended partitions for the more robust P4 logical channel. And so since there's no P3 logical channel in service mode MP1, we can get away with this, and we can basically double that throughput here on our new Q4, our P4 channel. So this is a recommended service mode. Now, if we could start from scratch, we would apply those special LUMB diversity and forward error correction techniques to every subcarrier. And if we did that, it would look something like this, service mode DSB1. Now, I'm just never going to stop doing that. Now you can see that we use all 28 partitions with our new P1 logical channel. And the existing service mode MP1 provides 98 kilobits per second of throughput. DSB1 provides a very robust 114 kilobits per second throughput. However, if you go to 16-QAM, that throughput jumps to 229 kilobits per second, or even 320 kilobits per second throughput, digital throughput on the HD radio channel. So nearly all, virtually all, maybe all media are now completely digital, except for one. Now, we're hoping that someday broadcasters will turn off their analog signal, and in its place, in the spectrum that's vacated by it, place additional digital subcarriers to provide more capacity. And that's why we developed this new service mode, MS5. And MS5 is basically service mode DSB1, which I just presented, except for it's located in the secondary spectrum where the analog would have been. And one thing you notice here is the level of these secondary subcarriers is much lower than the primary, and that's because the first adjacent primary digital signal is co-located spectrally with it. So since it's secondary, we have to keep that level low. Now, of course, if there were no first adjacent there for that station, perhaps those sidebands could be increased in level. Okay, so now let's get to the meat of it, which is what is the actual performance of these new service modes. So what we did is we ran simulations in 2 different environments. We started with a very benign environment, additive white Gaussian noise, or AUGN. And that's basically a stationary, unobstructed receiver. And we also tried a much more challenging environment with fast fading and intermittent outages in the signal. And that's meant to model, say, city driving or driving in the mountains, a much more challenging environment. In fact, we've kind of bracketed the performance with these two environments. Actual performance in the field with a moving vehicle is probably going to be somewhere in between these. So here's the results. We just selected 2 service modes to look at, one backward compatible and one non-backward compatible. We'll start with the backward compatible MP1X. And if you recall, we have our 4 extended partitions on either sideband. And that provides 34 kilobits per second of additional throughput. Now, if we reference that to kind of its cousin with the existing service modes, which would be MP3, the P3 logical channel, that provides 25 kilobits per second of the digital throughput. However, the big difference here is in robustness. And if you look in the stationary case, the MP1X is 3.5 dB better than the MP3 P3. And in the driving case, it's almost 7 dB better. So much more robust. And if you consider the fact, as just as a rule of thumb, that a dB of performance is roughly a radial mile of coverage, that's a lot of coverage area here. So it's impressive results. And now a broadcaster might say, look, I have enough robustness. I really don't care about that. I want bits. I want throughput. So in that case, he could then transmit service mode MP1X 16 QAM instead and double that throughput. And we're only talking about the throughput in the extended channel here. So double that to 69 kilobits per second. So that's good, but remember, when you go to higher order modulations, you get more constellation points, right? And we're jamming all this information into a small space. It's less robust. And yes, we saw that in our simulation results. In fact, now in a stationary environment, we're about 1.5 dB worse than service mode MP3. And in a city or just a mobile environment, we're actually still about 1 dB better than service mode MP3. The results are probably going to be somewhere in between here. It's kind of a wash. And so we can say that with robustness similar to service mode MP3, the P3 logical channel, service mode MP1X 16 QAM is going to provide 69 kilobits per second throughput as compared to just 25 kilobits per second today. Pretty much the same robustness, 69 instead of 25. Plus, you get fast tuning on your digital channels. Now, if we went to our new service mode DSB1, this is our non-backward compatible service mode. In this case, we're using all the subcarriers, the primary subcarriers, and we're broadcasting, and we get 114 kilobits per second throughput. If we compare that to service mode MP1's P1 logical channel, that gives you about 98 kilobits per second throughput. So we've got a gain in throughput there. And again, the robustness, though, we have a 3 dB increase nearly in robustness versus MP1 and almost 9 dB in the mobile channel. So again, a very large increase in robustness, and the broadcaster could trade that for 16 QAM instead to get more throughput. If he did that, that throughput doubles now to 229 kilobits per second. Again, that's compared to 98 kilobits per second for service mode MP1. So again, if we look at the results in terms of performance and robustness, This ends up being 2.5 dB worse, 2.6 dB worse than service mode MP1, P1 in the stationary environment. However, in the driving environment, it's almost 3 dB better. Again, this looks kind of like a wash. So we could say that with a performance similar to what we have today, service mode MP1, P1, similar robustness, instead of 98 kilobits per second, if we use DSB 116 QAM, we could have 229 kilobits per second. If the broadcaster decided, hey, I'm going to turn off my analog signal and transmit service mode MS5 in the secondary region, you could add another 114 kilobits per second for close to 350 kilobits per second of throughput. So this is the digital future. So just a little insight into why DSB1 QPSK was so much more robust in that fading and blockage environment. You can see here that with this diagram, what we have is a signal level versus time, and you can see the signal moving very rapidly due to fading. But every so often, we have these outages. These are the outages that we inserted randomly into the signal, a few seconds of a deep blockage caused by an overpass or something. Okay, what you notice with service mode MP1, though, is coincident with each of these outages, that's where you got your digital dropouts. And those would basically be blends in the MP1 system with that service mode. However, with our new DSB1 service mode, we had no dropouts. That's why it's so much better. And this is because of diversity. It's the time diversity, especially, to skirt around these outages. And it's because of the special forward error correction techniques that we're using. So in conclusion, we can increase our capacity of our HD radio signal, and we can do this for future data applications. Who knows what those applications might be, but we all know that there's autonomous vehicles coming, and they're coming fast. There's things like digital video, or surround sound, many different applications out there that perhaps could take advantage of this. In the near term, we could use service mode MP1X to improve our throughput. Eventually, we could turn off the analog signal and use service mode MS5, which is a very robust secondary service mode. Or we could even go to a non-backward compatible service mode DSP1, and that would give us the best robustness and throughput. So again, this is all just research and development at this point, but we're very excited about these results. And I might add that you won't find it in the proceedings, but we do have a companion paper that goes into much more detail on all of this. So if you're interested in that paper, you can just reach out to me afterwards and give me your contact information. I can send that paper to you. I guess we must have got it in too late to make the proceedings. Maybe we'll get it in the transactions instead.